Okay. So hello everyone. We have today with us a very special guest. We have Nicola, who was the very first and so far the only participant from Palestine IMO. And Nicola, you did very well at the IMO, right? You got an honorable mention and you were close to bronze, right? Um,
Yeah.
but yeah, so we just want to hear a little bit about your experience, what motivated you to study mathematics, and yeah, what it was like for you. So yeah, maybe you can start by introducing yourself so everyone knows who
Yeah,
you are.
so the very first beginning was like there was a mathematics researcher. He's originally Palestinian, but he's living in France. So they announced that there will be a competition and like a math camp, and I said, why not? Like just from the school and you know. So when I took part, when I did the exam, they contacted me and told me that I was going to the camp. So there I met many students. One of them was Adham a lot of years ago. So that's why I'm shocked to see him again. So, anyways, that researcher he brought a German IMO competitor to mentor us, teach us some stuff. And at this point, the type of math I saw in the Olympiad, I realized it was very different from what we learn at school. And I just fell in love with it and decided to continue from that time. I was around maybe ninth grade, something like that, or 10th. And from that time on, I just continued to read books and prepare for IMO. And then I met Samad, who gave me the opportunity to participate in real.
So you started in eighth grade was math camp. You pretended it was in eighth grade. That's when you started, got
Ninth, 10th,
inspired.
something like that.
Ninth. Okay, that's when you got inspired to study mathematics. Yeah.
Sorry?
That's so that math camp in ninth or tenth grade. That was when you were inspired to start studying math.
Yeah, yeah, yeah.
Um, I see. Um, and then yeah, from there, how did you? I mean, to go to the IMO, it's a long journey, right? From just going to a math camp to IMO. That's um,
Well, actually, things are a bit complicated. I was also involved in the informatics Olympiad. So, the same way, one of my teachers at school, our technology teacher, he told me there was a Palestinian informatics contest, and I went there absolutely knew nothing. I had a few time to prepare, but then I met the best programmers of Palestine, and they told me about a website called Code Forces, where all competitive programmers practice and apply what they learn. And from that point, I started diving deeper, and I was actually in that time more focused on informatics than math. But however, throughout my training, I was like more focused on the mathematical aspects of what I do. Anyways, around after that contest that happened when the Palestinian contest when I was like 10th grade. After it, Summit contacted me. He was looking for new students like to mentor. Since then, I knew Summit and we kept in contact. He was always like checking up on me, how was my training going, and so on. And I just told him. So basically, let's say that until now, all I've said is how I got into the community, how I got to know everyone. So from that point on, I just kept practicing and told Summit, hey, I think I want to participate in IOI, IMO. He offered me to do so. And it's simple, kind of.
Um, yeah, I'm sure it's not that simple, but and yeah, maybe you can say a little bit about maybe how did you train? Like, what motivated you to keep training? Because I know, it's hard to, for Kareem and Karam that just joined, Nicola got an honorable mention in at the IMO, which is a great achievement. And, sort of what motivated you to keep training? How did you train? Like, even like, do you have like specific advice because, we have four students that are training, right? And they want to, follow you, right? So um, do you have any advice for how you trained? Things like
Yeah,
that.
yeah, sure. So the motivation is simple. I told you I just fell in love with math, and that was my motivation. I was kind of addicted to math, you know. So just wait a minute, wait a minute. The guys in the dorm are making some noise. Just 1 second.
No problem. By the way, it's for everyone else. If you have any questions, please feel free to interrupt me or even Nicola and ask. Um,
I don't know. I told them I had a meeting, but they didn't listen. So how I train? Uh, so there were two aspects of training, gaining the theoretical material and applying it. So the sources I used for knowledge were mainly books. Like I just go look for the best combinatorics book for IMO preparation. I go through it. I solve the problems in it, read the theorems, understand them, all of that. And the same for the rest of the number theory, geometry, and algebra. Although I give more attention to combinatorics and number theory. That was a mistake actually because the 2022 geometry problem was the easiest, and I couldn't solve it because I didn't pay much attention. So that's a point that I would like to tell you about. Um, so yeah, I was reading books and then solve the problems in the books and going to websites where I can find like old IMO questions and try to solve them. And it takes so much time solving a problem. Sometimes it took 3 hours, sometimes two, maybe five. Some problems were hard that took like maybe a whole day. I just leave it and return the next day. So throughout your training, if you find a problem difficult, yeah, I mean, you just don't give up so early. Just try and try, but also don't waste like a lot of days. And if you can, just see the solution. But when you solve a problem, you make connections. Uh, what are they saying in the chat?
mm,
Uh, okay, someone sent me. Okay, okay, we can talk later. So anyway, that's it. Solving IMO problems and reading books.
okay, great. And it seems like you were training like every day for like several hours, right? If you train one day, you solve
Yeah,
a
yeah.
problem, you come back. Yeah. Okay. Um, yeah. Okay. Um, yeah, so I want to give a chance for everyone else to ask Nicole. And also, if you want, the others, you can introduce yourselves as well. This is a chance for you to talk to Nicola if you want. Um,
Abdullah and I already know Nicola.
oh, okay, great. You guys,
Yeah.
okay, I didn't know. Um, okay. Um,
How many hours on average would you say you were training for the IMO?
Well, on average, I had like a routine schedule.
Yeah.
On holidays,
Yeah.
Friday and Sunday, I just had the whole day, literally.
Yes.
And for the other days, I had like 3 hours to practice, 3 to 4. So I solved like maybe 3, 4 problems, something like that.
Okay.
Ahmed told you that like to prepare questions, didn't he?
Um, Hi, actually, I have some question about uh, especially the combinatorics problems. How could you like get the motivation to do some steps there, solve a combinatorics problem to should try some coloring or something like this? Uh, how could we get the motivation to do these steps?
I didn't get your question exactly.
Uh, I mean,
Are you asking like how to approach a combinatorics problem?
yeah, and get the motivation beyond the steps, the key steps and key ideas.
And how to get the key steps? Well, that's a very general question. I don't know from where to start, but I don't know. Like, if you wanna ask about this, you gotta give me like a specific problem. But generally, it all depends on your practice and problems like that you saw before. You can't reinvent the theorem on your own. So you have to see similar ideas. Of course, every question itself has a new aspect or the creative one. For that, you just give it. You take time. You take examples. Well, yeah. Actually, examples are a very important thing in solving the problems. So yeah, you now I remember how I used to solve combinatorics problem. So I take examples on like small n to try to figure out how the system works, how things are going. And so based on the examples, I try to put some assumptions or like, yeah, maybe it goes like that, maybe like that. I don't know. So for each of these assumptions, I either try to prove it correct or prove it wrong. Proving it wrong might take an example. And if I prove something correct, then I am sure I am one step forward towards the solution. So yeah, important and something important is examples, and yeah.
Thanks, Nicola. That's a very good answer. I how to solve combinatorics problems. I really appreciate it.
Thank you. Any other questions?
Do you think that it's better to focus on like 2 or 3 subjects or one subject or focus on all subjects?
At the time, I prefer focusing on one subject at a time, but like not take like for example, assume you have 1 year to prepare. You don't just divide it 3 months for this, three for that, and three for that. Like you don't want to practice, like for example, combinatorics in the first 3 months, and after the year ends, you're not ready. You don't remember anything. So yeah, you should divide the year into periods. Every period you focus on one subject, but and in like maybe 1 month, maybe you take a month for combinatorics, and you don't focus really on the other materials. You like if you saw a question, of course you're gonna see let's say a number theory question, and you'll be very curious to solve it. Yeah, you solve it like, but it's not like a main part of your schedule. You just solve them on the side. And of course, everyone has his own schedule. Maybe Tahsin knows better than me.
Actually, I wanted to ask you a little bit because I didn't train for the IMO specifically, right? I only trained up to some national level things. So do you have any advice for how to actually for how to make your own schedule for training? Because that's very because maybe everybody wants to put in a lot of hours and train, but how do you actually build an effective schedule? And also, keeping in mind, how do you build an effective schedule if you have, say, 1 year to train versus I have 3 months to train because the IMO is in 3 months, right? So maybe you can say something a little bit about that.
If I had 3 months, like a short amount of time, I think I wouldn't have like enough time to get better in all the subjects, and in this case, I might focus on my strength. So let's say I'm good at combinatorics and number theory. I solve a lot, like to make sure I am fit for the contest. That's if I had a short amount of time. But for a year, if I had a whole year or more on the long term, as I said, I just prefer giving each subject a month or until you get bored of it. But like you don't just get bored every couple days, and that doesn't work. You should give it a good amount of time, like to feel the subject.
Okay, thanks. That's very helpful. Thank you, Nicole. Um, um, maybe I'll ask one more thing. Because this is something I struggled with when I was training was okay, sometimes training goes well, you're very motivated for several weeks, but sometimes, there comes a few weeks where you really don't want to do, you get bored, right? So what do you do then? I don't know. Because in order to do well in IMO, you really have to train consistently, right? So how do you stay motivated?
Um, well, as far as I can remember, I love to think a lot that I had no periods where I lost motivation, but I'll tell you about something else. At many points throughout my training, I uh, I was struggling with hard problems and I couldn't solve anything. I felt I was like shit and didn't want like. It's not that I didn't want to continue. I always did, but I felt so bad. So what do I do in similar situations? I just take easier problems. Like when I solve easier problems, I feel like, yeah, I got it and good. And that brings me back with motivation.
Okay, thank you. That's a very good answer. And it's also, when you revisit easier problems, you learn things and you see things you didn't see before. So it's very
Yeah, one more thing, a problem that you solved in the past, when you return to it after you forget it, you'll find that it's a lot easier. That gives you an extra motivation.
All right. Any more questions?
I have questions about how to make my solutions more understandable. Sometimes when I solve a problem, then return it to like after a week or 2 weeks, I find it hard to understand the solution. I take some time to understand it.
So you're asking how to make your solution neat and easy to understand, right?
Yeah.
Well, I had the same problem as you, and here are some tips. Well, after I get the solution in my mind, I don't just start writing it down. I take an extra, I don't know, extra 10 minutes, 15 minutes, I don't know, to think how should I write it, how to make it look more neat. And in addition to that, a key factor that you could use is redefining things. So let's say you are dealing mainly with the number of ways to do this and that under the condition that A holds and B doesn't hold. I don't know, something like that, something long. You just define a new variable. You say S is the number of ways to blah blah blah. And throughout your solution, you just write it over and over. You use S. So redefining and taking extra time to sort out your brain and clear things. These are two main things.
Thank you, Nicola. That's very good advice. Mm. Okay, do you guys have any more questions for Nicola? Okay, then so if you have more things you want to ask, you can send me and I can forward, or you can maybe, I don't know, maybe there's a way of contacting Nicola directly. It's up to you. Yeah, but okay. Thank you, Nicola,
Yeah.
for
But actually, I have one extra question.
okay, yeah, please.
I want to ask Nicola about how did he manage to balance between studying for توجيه and training for the IMO and II.
Well, that depends on you. What do you want to do with Tawji? Like, if your goal is to be the number one on the whole country, then it's actually difficult to maintain. For me, I wasn't that interested. I just wanted like to pass with a with good grades. And my priority was preparing for the IMO. So, but anyways, I didn't neglect the Tawji. I like once I get home, I just study quickly. I prepare for my exams and so on, and I leave at least 3 hours for training every day. And also well, after those 3 hours, I revise a little more for the exam. And you can create more time by yourself. Like maybe before you sleep, you think about something stuck. Maybe in the break between the lessons, like you just create time for yourself and ask yourself what is your priority.
Okay, thanks.
Welcome.
Hey, Karam, do you have any other questions for Nicola?
Actually, no, I don't have.
Okay. All right. So yeah, thank you, Nicola, so much for joining us. If anyone has any more questions, feel free to forward them to me. But I guess yeah, that concludes our session here. Yeah, so thanks a lot, Nicola. I think this
You're
is very
welcome.
helpful
Thank
for
you too. And
I think
nice
this is
to
very
meet
helpful
you.
for this team. Yeah, it's nice, very
If you
nice to
have
meet you too.
if you have any more questions, guys, you can like contact me. Some of you might have had me as a friend on Facebook and other social media. You can contact me if you have anything else. So yeah, keep it up, and thank you for having me today.
Thank you, Nicola. All right. Great. Yeah, so let me pause. So let's share my screen. Okay, so we're going to talk about notation for three variable polynomial inequalities. So we'll focus on three variables because it's very common in the IMO and because hopefully it gives some intuition for how to think about higher variables, right? So yeah, so I want to introduce some kind of graphical notation that'll resolve questions like when can I use AM and GM? Like, okay, so I know like if I have symmetric polynomials and I have this mirror head condition, I can use AM GM. But what if it's cyclic? What if it's more complicated? Like, how do I know when to use AM GM and these kind of things? And hopefully this will clarify that. Also, it'll explain things like when can I use, various other, we'll talk about Schur's inequality and sum of squares. So we'll talk about some other things as well. Okay, so let's start with this. So how do we visualize this polynomial, right? So three variable polynomial, x cubed plus y cubed plus z cubed plus 3xyz. So the point is you want to put the terms in a equilateral triangle. So I'm going to draw a triangle like this. Okay, and so the point is that it will be like this. So you'll have x cubed here, y cubed here, and z cubed here. Okay. And then I'm going to put all the other, so these will be cubic monomials. So I'll put all the other cubic monomials in this grid. So there's going to be x, y, z here, and then what? And then the rest will be, yeah, so x, y, z goes in the center, and then here will be the polynomials in x and y. So those will be x squared y, xy squared, and then x squared z, xz squared, and then here we put, y squared z and yz squared. Yeah. Okay, so if you wanted to, so if you want to, sort of visualize this polynomial, the way I would do it is I would write something like, so I would write like this, I would write, so I put 1, 1, 1, and then here I put 3, and then the rest I put 0. Yeah, and so this here is some kind of notation for this polynomial. Does it make sense how we are notating polynomials?
Yeah.
Okay. And have you guys seen this before, this notation?
I haven't.
Okay. Yeah, so it's helpful. So okay, maybe I'll do like maybe I'll do one more thing, and then we can sort of yeah, okay. Yeah, I'll do one more. I'll do a bigger polynomial, and then we can talk about how do you actually use this notation. Right? So Okay, so here we have a degree 6 polynomial. I'll put the vertices first. So it's degree 6, so we'll have x to the 6th there. And then let's see, 0, 1, 2, 3, 4, 5, 6. So it's y to the 6th here. And then 0, 1, 2, 3, 4, 5, 6. So I'll have z to the 6th here. But these are all 0. And then we have what? And then we have this symmetric term. So it'll be 6 terms that are here, 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 and here. And then we have this term here, which is going to be in the center. So 3, and then everything else is 0. Okay, so, all right. And maybe I'll just talk about what is this, what is like a symmetric polynomial? So, so what does it mean symmetric? So the point is, okay, here's your triangle, right? So, for example, let's see. So we have x to the 6th here, y to the 6th here, z to the 6th here. So when I reflect along here, that's switching y and z. When I reflect along here, that's switching x and y. And when I reflect along here, that's switching x and z. So like, what is a symmetric polynomial? It means that if I have some term, then I should have all of the reflections. So I'll have up to 6 different terms. Or these are the reflections along these 3 axes. That's what a symmetric polynomial looks like. Does it make sense what I'm saying?
Yeah, but how do we use it?
Okay, so I'll get there, but maybe I'll ask one thing. What does a cyclic polynomial look like in this?
Yeah, I was gonna ask that too.
Yeah, okay, so first let's understand, what does a cyclic polynomial look like? So if I have some term like green or something like here inside my triangle, can you see it? Oh no, it went away. Yeah, so I have green, right? What is the cyclic?
Then if we rotate it, it like it doesn't change.
That's right. Yeah. So if I whatever this monomial is, the cyclic ones will be the rotations by but not by 60 degrees, by 120 degrees.
Yeah.
So exactly. So I will I skip one of the so my term was here, and then I skip this, and then I go to here, right? So it'll be here, and then here, and then here, something like that. So there'll be they'll form an equilateral triangle, center at the center. Yeah. So that's what cyclic looks like. Does it make sense?
Could you explain again how cyclic looks like?
Yeah. So cyclic means that your polynomial, it should be invariant when you rotate 120 degrees. So if I have some term, I should have 120-degree rotation of that term as well. Right. So maybe I can just do like an example or something, right? So let's do let's put some numbers or something, right? So right. So yeah. So oops, that's not right. Here we go. Yeah. So this is x to the 6th. So let's actually identify one of the terms here, right? So let's identify this term here. So it's so it lies along x and y, and it's 2 steps over. So it should be x to the 4th y squared, right? Okay, so we have x to the 4th y squared, and then when you rotate it, let's say it's getting a little cluttered, so I'll delete some things. So let's delete these because they're not helpful, and maybe let's draw in the whole boundary of the triangle. So when you rotate x to the fourth y squared, it lands here, right? And this one is going to be z to the fourth x squared. And then the other one will land here, which will be y to the fourth z squared. Does it make sense now, Karam, how this works?
Yes, it does.
Yeah. Okay, good. So yeah, this is it's important. Like it's okay, like cyclic polynomials really look cyclic, like they're invariant under like cyclic rotation, and symmetric polynomials look symmetric. They're invariant under all the reflections. Okay, so let's talk about how to use this. So the first thing I want to talk about is visualizing these sort of mirror-head type arguments, where you use weighted AMGM, but visualizing it using this notation. So yeah, so I'm going to put this away for now. Let's focus on the inequality here. So this inequality, okay, I think it's you can just directly apply AMGM, but let's just see what it looks like when we do when you use this notation. So yeah, so the left-hand side is x to the sixth, y to the sixth, z to the sixth, and the right-hand side is this cyclic sum. I'm going to go ahead and notate both on the same triangle. So I'll do it like this. I'll write, yeah, so that's x to the sixth, 0, 1, 2, 3, 4, 5, 6. So there's y to the sixth, 0, 1, 2, 3, 4, 5, 6. So here's z to the sixth. Okay, and then I'm going to put these on the same triangle as negatives. Yeah, so where is x cubed y squared z? So, okay, so x to the sixth is here, and x to the 0 is here. So x cubed will be here. Okay, and then which one will it be? It will be the one that's closer to y, so we'll draw it here. Okay, so that's x cubed y squared z. I'll draw -1, and then we have the rotations of that. So yeah, so where are the rotations? Okay, maybe it'll be helpful if we draw the center. So the center is so the center is 0. It's not 0. It's not part of the inequality, but now we know that the other terms are here and here. -1, -1. Okay. Okay. So this is the inequality. We want to show that this is greater than or equal to 0. Yeah. I won't write greater than or equal to 0. I think it's very good. You guys see how the whole inequality is notated by this diagram, yeah?
How
Okay.
how would it imply that it's bigger than 0? What's the
I haven't proved it yet. I've not proved it, but I will now explain what is the proof, right? So the proof when we do weighted AMGM is like this. We say, okay, we want to write this monomial as a weighted mean of these, weighted geometric mean. So we write 3/6 times x to the sixth plus 2/6 times y to the sixth plus 1/6 times z to the sixth is greater than or equal to, then we take so that's the arithmetic mean, we take the geometric mean, and we get exactly what we want. We get x cubed y squared z, okay? And then what do? We sum this cyclically. So we do a cyclic sum of this expression, and we get exactly what we want. We get x to the sixth plus y to the sixth plus z to the sixth is greater than or equal to cyclic sum x cubed y squared z. Okay. So really we're adding together, like there's 3 inequalities we added, but let's just write one of them. We have one of them here. So that inequality by itself, how would I write it? I would write it as I would write it as I have a 3/6 x to the sixth. Then I have 0, 1, 2, 3, 4, 5, 6. 2/6 y to the sixth, and then 0, 1, 2, 3, 4, 5, 6. 1/6 z to the sixth, and I say that defeats what? Here, I think, is the center. Yeah, that defeats. No, sorry, not center. I want to put that defeats what? This term, right? -1. Okay. So if I just have this one, I can write it like this. But what is this saying? This is actually like, you can understand this geometrically. It's saying if I have like some like masses here, 3/6, 2/6, 1/6, this is the center of mass. Does it make sense? Like you literally imagine putting weights of 3/6, 2/6, 1/6, and the center of mass of those weights is right there. Does that make sense? Like, this is also called barycentric coordinates in geometry. I don't know if
Okay.
Yeah, but like, what's the point of the triangle itself? Like, would it give us insight into a certain thing?
Well, I'm getting there, but I'm getting there, but I just want to understand, like, does it make sense that this here is like okay, like these are okay. Wait, maybe I'll just continue and then it'll make sense. So so okay. Now let me ask a slightly more slightly different question. So let's say let's say I do this. Let's say I give you x to the 5y. Maybe it's on the next page, yeah? Okay. Let's say I give you x to the 5y plus y to the fifth z plus zx to the fifth. So this is a cyclic thing. And I don't tell you what I put here. I'll just put some cyclic of x to the p, y to the key, u, z to the r, something here. I don't know what they are. So now let's plot this. So I have here, so that's x to the sixth, 0, 1, 2, 3, 4, 5, 6. Y to the sixth, 0, 0, 1, 2, 3, 4, 5, 6, z to the sixth. Okay. And then I have x to the fifth y is here, y to the fifth z is here, and the x to the, oh, sorry, this should be z to the fifth x. Z to the fifth x is here. Okay. And now I ask for which PQR with some 6, I should assume, so I assume P plus Q plus R is 6. So for which cyclic sum, so it means I pick some point in the triangle, and then I look at the rotations of those points. For which, so for which P, Q, and R can I prove this inequality using AMGM? That's my question.
Are they the ones that make a standard polygon in the middle of the,
What do you mean by
Maybe.
standard polygon?
like, equal size, equal angles?
But they always will, right? Because I'm just if this is my point PQR, right? So if this point is PQR, right? Then so when I do the cyclic sum, these other two will just be the rotations
Oh, yeah,
around
they
the
will
center.
form a triangle either way.
Yeah, so they always form equal outer triangles. But my question is, when can I prove this inequality using AMD? So let's take a step back. let's ask the question for the previous case. So let's say I wanted to show that x to the sixth plus y to the sixth plus z to the sixth is greater than some cyclic sum. X to the p, y to the q, z to the r. Oops. Where p plus q plus r is 6, and they're all greater than equal to 0. So I know that they live inside of this triangle, right? Right. So then the other ones will be like here and here, some rotation. So I know from AMGM I can always prove this. Yeah, I just take the weights are p over 6, q over 6, and r over 6, right? That makes sense?
Yeah.
But geometrically, what it's saying is I can always write this point as a weighted mean of these three. So no matter what point I have, as long as it's inside my triangle, so I have some triangle here. I'll draw it in blue. This is my triangle of like, monomials where all the weights are where all the exponents are positive or non-negative. As long as the red point, this x, the p, y, the q, z to the r is inside the triangle, I can always write it as a weighted mean of these three. Okay. So if I look here, I can ask the same question. So of course I have the big triangle, which has vertices x to the 6, y to the 6, and z to the 6. But I also have the smaller triangle, which is vertices x to the 5th y, y to the 5th z, and z to the 5th x. And my claim is you'll be able to do this as long as the red point is within the blue triangle. That means you can write it as a weighted mean, a weighted like arithmetic mean of those 3 points.
I see.
Does it make sense?
Yeah.
Yeah. So it's a general thing, right? If I give you, sort of, you can forget about the grid. If I just
But the smaller blue triangle must be equilateral.
Well, it's automatically equilateral, right? Because what is it? It came from a cyclic sum, right? Does that make so? What is the blue triangle? It came from here, right? So it came from a cyclic sum, so it means it's this point, and then I rotate it 120 degrees and 240 degrees. So it must be equilateral triangle. Do you see?
Yeah, because we have the other 3 triangles must be congruent, so the 3 sides must be equal.
Yeah. But you can also think like what how did I build this? Like I built this by taking like this guy here, and then I rotated 120 degrees. So if I take like if I have a point and I rotate it 1/3 of the way around and 2/3 of the way around, it'll be an equilateral triangle.
But why this implies that the triangle must be equilateral?
It's like this. I have a point, and then I have another point, right? And then I draw this point. It's 120 degrees. These are equal, and then another one 120 degrees. These are all 120 degrees, and then these are all equal. So then these 3 triangles are congruent, yeah. This, and this are congruent. Does it make sense?
Yeah, yes.
Yeah.
Can this also help us find weights?
It can, right? So what you need to do, so let's do it can help you. Yeah, okay, it can. So Yeah, let's talk about how it can help you. You can also just like, okay, once you know it's possible, like once you know the red point is inside the blue triangle, you can say, okay, I'll use linear algebra to calculate the weights, right? I'll write the equations. But you can also think like this. So, yeah, so I have this point. Maybe let me make my diagram less cluttered. So let's draw here, right? So I have my red point here, yes. Okay, great. So I want to write this red thing as a weighted combination of the green of the other things, right? So okay, what will be the weight from this vertex? So if the weight was 1, it would have to lie along this line. Sorry, that's this line. And if the weight was 0, it would lie along this line. So the weight, it will basically be, I look at this distance and I compare it to this distance. That's the weight. Does it make sense?
Can you show it again?
Yeah, maybe I need to draw something. So let's maybe gray is okay. No, let's do green. Okay. So this will be the things that have weight 1 with respect to this vertex, right?
Yeah.
And this will be the things that have weight 0 with respect to that vertex.
Yeah.
So in order to find the weight, I need to figure out how far in between these lines red lies, right? And so the weight is going to be the ratio of this distance to the total distance between the lines. So let me say it again. It'll be sorry, let me just no, I'm sorry. It'll be this distance divided by this whole distance.
Yeah. Okay.
Because if this ratio is 0, it means it's here, so we get 0. If this ratio is 1, it means it's here. Yeah? So it's like that. Does that make sense?
Yeah. So if it's in the middle, if it's ABC, it's always a ratio of 2 and 1.
That's right. So it'll be 1/3, 1/3, 1/3. You'll have 1/3 weight here, 1/3 weight here, 1/3 weight here, in the middle, always. Yeah. Yeah. So this kind of this is called these. Okay. If you want to read more about this, this is called barycentric coordinates. Is what this is called. Okay, but it's kind of intuitive, but you have to get used to it. Is what it is.
Is there
Yeah. Go ahead. Alan.
is there a way, for example, like look at the coefficients and add a triangle and figure out if it's correct or not?
What do you mean? Look at it. Do you mean I look at an inequality? Like I look at an inequality like this or something. Sorry, like this for example. Where did it go? I lost my page. Oops. Sorry. Okay, so you're saying I look at some kind of thing like this. Sorry. I lost my page. Okay. You're saying you want to look at something like this and see just like an algorithm to see if it's correct?
No, like for example, if you have a full inequality, like for example,
Yeah.
well, the one we were solving some moments ago, the one
Yeah.
by weighted AMGM.
Yeah.
So we put it in the triangle. What tells us that this would be correct? Like what would tell us that this inequality is actually true?
It's not obvious, right? It's not like there's some what you like. It's like this. You let's see. It's not like I can just look at it and tell. You have to sort of okay. What I'm trying to explain is how do you all these things we do with inequalities, like when we do weighted ANGM, how to do it pictorially. Because once you do it pictorially, you'll start to understand, like, what I'm trying to say. Like it'll be clear what kind of like steps you can take. So like I when I look at this inequality, okay, how do I know it's true? I know it's true because this point lies inside of this triangle. Okay, so it means I know I can write a weighted AMGM argument to show that this red is smaller than this black. Does that make sense?
Yeah, but that was only the case because the coefficients are 1. If they weren't 1, then it wouldn't necessarily work with the
Yeah. So then we need more tricks. We need more tricks. So right now, all I'm trying to explain is how to compare symmetric, like cyclic sums with each other. Then I'll talk about some more tricks you can do. Yeah.
But does this tell us that any cyclic inequality like this, like when we have in the left hand side all the powers are 6, and all the other powers in the right hand side uh, are summed to 6, but they are less than 6. So they must uh, then the left hand side must be bigger or equal to the right hand side always, because the points will always lie inside the triangle.
You're saying if I have more terms on this side?
I mean this. If the left hand side was x to the 6 plus y to the 6 plus
Yes.
to the 6,
Yes.
then it will work for all b and all triples b, q, and r.
Yes, this is true. Yes, because you always lie inside of this outer triangle. Yeah, this is true. Yeah.
Another question. I think
Adam, let me say, yeah. So in some sense, kind of what you're saying is this is the strongest like cyclic or symmetric polynomial we have, right? It's bigger than everything. But you also kind of knew that because that we proved it before using weighted ANGM, that like whatever you put here will always be less than or equal to whatever you put here, as long as you have the same number of terms on each side. But when I think of it pictorially, it's because yes, this point, this cyclic polynomial always lies inside of the triangle for that cyclic polynomial. Okay.
But what does it mean that some point lie inside some equilateral triangle?
You mean like here?
Yeah.
What do you mean? What did like? Can you like? Are you saying? You want to write a formula in terms of like PQR and like P prime, PQ prime, R prime? Is that what you mean?
Yeah. So when the formula is true, the point will be inside the triangle.
Yeah. So that's a good question, and let's say I don't know the answer. So I'm going to say that's homework. Homework is determine. I don't know. I think it's possible, but I don't know. I mean, you can always draw it, but yeah. So determine.
Would it be related to majorization?
So we'll get to major. It kind of. I think the correct answer I'll say is not exactly. So I'll explain what majorization is. So maybe I'll delete this now and then ask me again after I explain what majorization is, right? So it's a great question. So we'll get there. Adham, you had a question.
Yeah. So let's say like the inequality that we know is true, right? Like for example, a minus b squared is always bigger than 0. And we write it out in this Chinese notation. It would be 1, -2, 1, and the others are 0.
So actually, so Adham.
No, that's my question. My question is for any other small triangle of a big triangle, will that also always be true?
So the answer is yes, and actually I'll get to it. So you asked an excellent question, and it will explain the second part of Rauter. So let me first wrap up this stuff about Muirhead and symmetric polynomials, and then ask your question again, because I'll get to it. It's an excellent question. Okay, so let me just give one more example of this. Yeah, so we did this one. What else we do? What else? Okay, no, before I go there, I want to do something else, which is okay, so we did this example, but let's do something a little bit different. Yeah, so we know, okay, yeah, so this was the question we just did, like for which ABC can you prove this? And the answer was, well, yeah, the answer is, well, it should lie inside of this triangle here, right? That's the answer, right? So yeah, it should lie inside of this blue triangle. let me first copy this actually. I'll come back to this later, but for now, yeah, so for now, the answer is multi-lines.
Will this idea work for irrational numbers?
Yes, it will all work for rational numbers. The only reason I wrote integers, in fact, it will work for irrational numbers as well. The only reason I wrote integers is so that I can actually write so it's easier to write them like the coefficients. Like that. That's why I chose integers. But it's not important that they're integers. And actually, I usually scale the variables. Like I'll replace, if I have x to the 1/2, I'll just write x to the 1/2 equals like x prime. And so I always want to work with integers just because it's easier. Okay, so we answered the question of, when can you prove using AMGM that this is true? But let's think about what if I had a symmetric. So what if instead I asked, when can you prove that the symmetric sum x to the 5th y exceeds let's not do the symmetric sum. Maybe we should do, now let's think. So no, let's do the symmetric sum. The symmetric sum of x to the a, y to the b, z to the c. Okay. So now what are we comparing? Yeah, so now what we have, our inequality is actually bigger now. So we have these terms. And now, okay, so that's the left-hand side. And then for the right-hand side, it's a symmetric sum, so it's not just enough to have the rotations. We need to have like the reflections along these axes. Right, so that'll be the symmetric sum. Yeah, so it'll be something like this. So notice this is not, these points, they're not going to form a regular hexagon. They will form an equiangular hexagon. Do you guys see what I'm saying? So they'll form like all the angles of the hexagon will be 120 degrees, but the sides will be, it'll be a long side and a short side. Okay. Yeah, so now can you tell me, for which ABC will you be able to prove an inequality like this using weighted AMGM? So if we were to prove this using weighted AMGM, what we would have to do, we would have to write W1 x to the 5th y plus W2 xy to the 5th plus W3 y to the 5th z plus W4 y z to the 5th plus W5 x to the 5th z plus W6 x z to the 5th is greater than or equal to, and we'd want on the right-hand side x to the a, y to the b, z to the c. Okay, and then we basically add this symmetrically, and we get the inequality we want. So what you have to do is you have to write this one thing as a weighted sum of these 6 vertices now. Does that make sense? So the condition is that this red one should fall inside of this hexagon.
Maybe we'll get some system of equations.
So there'll be a system of equations, but what is the system of equations saying? Ultimately, it's saying, I want this. So what is this guy? So this guy here is x to the a, y to the b, z to the c. I want to express this as a weighted combination of these. Right, so where the weights add to 1, right? So some average of these 6. So you can write it as a system of equations, but the point is, like, okay, if I give you several points in the plane, it doesn't matter really where they are. What are all the points you can get by weighted combination? The answer is something called a convex hull. Right? You draw the okay, so let me yeah, so okay, this is a bit of a side comment, but this is important, right? So here, so I'm in the plane. Okay. I have a bunch of points in the plane. They don't have to be arranged in any nice way. And I ask, which points are weighted combinations of these? Does the question make sense?
Yes.
Yes.
And I'm claiming the answer is the following. The answer is the convex hull. So what is the convex hull? It's the smallest convex
But
polygon. Yes?
what do we mean by that they are what do we mean by points that are like sum of weights of them? I don't understand it
Yeah,
because
yeah.
what is the
Yes,
number of variables we're talking about?
So we're talking about points, right? So okay. So let's think. So it's either 2 or 3 variables depending on how you think about it, right? Because okay, all of these are they're all like A, B, C. They're all 3 variables. But the constraint is A plus B plus C equals 6. So they live in a plane. And
So
whenever I have
there are
yeah,
two variables. There are two variables.
you can think of it as two. You can either think of it as 2 variables or 3 variables with a constraint. Either way, we get a plane. Okay. And what I'm saying is in a plane, you can always talk about, okay, you can't talk about adding points in a plane like that because I don't know what 0 is really. That doesn't make sense. But I can talk about weighted average. So I can talk about, okay, if I have a point here and a point here, I can talk about, let's call it A and B. I can talk about 1/3 A plus 2/3 B. Okay. That's going to be the point that lies here, like 1/3 of the way between them. Does that make sense?
But what must it be here?
Sorry, I didn't understand.
Why the point must be here?
So I'm
Must be
saying
in
it's yeah. So I'm saying it's 1/3 of A and 2/3 of B, right? So it's you can even write it in okay. Let me just if you want, you can write it in coordinates, right? So like okay, if you maybe I need a new page for this. Okay, so let's write this add page after. So okay, let's put a coordinate system. There's really no coordinate system here because like there's no 0, but let's just put this. Okay, so now let's say my points are like yes is 1, 1, and then I have another point here which is like 4, 4. Okay, and now if I want to do 1/3 of A plus 2/3 of B, I can just use the coordinate system. I can say okay, this is 1/3 of 1 plus 8/3. I get 3. I'll get 3, 3. Okay, and so I can put it here. But really the point is that it's what is going on? It's 1/3 the way from B to A. So if I'm going from B to A, it's 1/3 the way along in that direction. Or if I'm going from A to B, it's 2/3 of the way along there. Does that make sense?
Yes.
So I didn't need the coordinates to do that. Like I can do that, like I can do this without coordinates. I can just say, okay, if I have 2 points, A and B, I can talk about there's a point which is 1/3 A plus 2/3 B, and it just means that okay, it's because it's closer to B and it's in the ratio 2 to 1, like this.
Yeah. So it does not require a coordinate system because the point will lie in the line AB.
That's right. It doesn't exactly right. And sort of the important thing is it's because these weights add to 1. That's why it's a weighted sum. Okay.
Yeah,
So I can do it.
but yeah. But what happens if we have more than 2 points?
Yeah. So now let's do 3 points. Okay. So let's do 3 points. For 3 points, I have A, I have B, I have C, yeah? Okay, so now what? Let's consider a point that's like let's write let's do something. Let's do 1/4 A plus 1/4 B plus actually let's start with something. Let's start with 1/3 A, 1/3 B, 1/3 C. Let's start with this. Okay, so the weights add to 1. So I don't, whenever the weights add to 1, I don't need a coordinate system to make sense of this. Okay, but why? So it means, okay. So first of all, okay, when the weights are equal, intuitively it means centroid, but let's see why. So you can write this as, let's rewrite it. Okay, sorry, my handwriting is getting bad. So yeah, let me just write it somewhere nice. So if I want to have 1/3 A plus 1/3 B plus 1/3 C, I can write it as iterative. So I can write it as first I take 1/2 A and 1/2 B, and then I take 2/3 of that and 1/3 of C. So when I do 1/2 A, 1/2 B, I get the midpoint. And then I do 2/3 from the midpoint to C. So I'll go here in a ratio that's 1 to 2. But we know this is the centroid. That's exactly where the centroid lies. Right? So when you do 1/3 A plus 1/3 B plus 1/3 C, you really get the centroid. Does it make sense, Kyle?
Yeah, but
And you
here
can
I
do this.
think we are assuming that ABC is equilateral. We
No. I don't need any equilateral here. This made sense without ABC being equilateral.
yeah, it must be the centroid.
Sorry?
The resultant point will be the centroid.
Yeah, it'll be the centroid. And do you see now how I can take a weighted sum of many points? I don't need to 3 point. It can be 5, 7, any number of points.
Yeah, I see.
Yeah. And the answer, the result doesn't depend on a coordinate system. Okay, so let's go back now. Now I have my points, right? And I ask, what are the things you can get as weighted sums with non-negative weights? Let's not have negative weights, right? So with non-negative weights, you take a weighted sum. And the claim is that you can only get the convex hull, or like things inside the convex hull. Okay. So for example, you can get the convex hull just by doing like weights, like okay, if I want to get this convex hull, I would do weights where these are all 0. Okay, and then this way I can get the entire convex hull, and then I can start going inside, and okay. So does it make sense what the claim is, at least?
Yes, but would we have multiple ways to get to one point if
Yeah.
we have this
Yes.
many?
Yeah, so if there's more than 3 points, you can very easily have multiple ways to get to a point.
Okay.
Like even I have a square, right? Draw a quadrilateral, right? There's going to be multiple weights that give me, like if I have some point here, right? There's many weights that can give me that. Yeah. Okay, so now let's look here. So yeah, let's look here. So the point was, in order to prove this inequality, we need to basically express one of these red points as a weighted combination of the black points. So it's going to be possible if and only if this red point is inside of the convex hull of these black points. Yeah. Does it make sense what I'm saying?
Yes.
Okay. So now now let me explain what Muirhead has to do with all of this. So Muirhead is basically the following theorem. Muirhead says the following. So suppose I have suppose I have A, B, C, and A prime, B prime, C prime, both with the same sum. Okay. And I order them A greater than or equal to B, greater than or equal to C, greater than or equal to 0. So what does that mean? It means when I draw the picture, they both lie in this this part. Yeah, so the condition that the A, B, C are ordered means that x to the A, y to the B, z to the C is lying in this part of the triangle. Okay, so I have 2 points in that part of the triangle. Black one is A, B, C, x to the A, y to the B, z to the C, and this red one is x to the A prime, y to the B prime, z to the C prime. And basically, Muirhead says that the red one lies in the convex hull of the black one, if and only if the majorization condition is true. That's one way of understanding what three-variable Muirhead says. So Karam, do you remember you asked me how do I tell if you give me a triangle and then if I give you something like this, how do you okay, so if I give you something like this, right? How do I tell if this one lies inside of the triangle? And you asked me if it's related to Muirhead. It's not. What Muirhead is about saying if this point lies inside of the hexagon. Does it make sense?
Can you go over it again?
Okay, so do you understand why this is equivalent to Muirhead, or why this is basically the same as Muirhead?
Because when we have a point inside this hexagon, it will be like expressed. It could be expressed as a weighted sum of the three of these points, these 6 points.
Yeah, exactly. Yeah. So now, before you had asked me, what about the case where I'm like talking about cyclic sums, right? So you asked me about the following. You asked me if instead, what if I don't care about the cyclic sum, but I care about the symmetric sum. So I care about when can you have the cyclic sum of x to the a, y to the b, z to the c, bigger than the cyclic sum of x to the a prime, y to the b prime, z to the c prime. And the point was that has to do with whether or not you live inside of this triangle. So the condition is not going to be related to majorization, right? In fact, it's an even stronger condition. Does it make sense?
Yes.
Okay. Yeah, so I guess there was some example here where, like, if I have something like this, then, the cyclic inequality won't be true, but the symmetric inequality will be true, right? So if the example is here where, okay, this is ABC and this one is A prime, B prime, C prime, then this is an example where even though Muirhead is true, x to the A, y to the B, the symmetric sum of this is more than the symmetric sum of this. A cyclic sum, it won't be true. Yeah. Does it make sense? So Abdullah, I think you asked me some question about this. Does it resolve the question you're having? Abdullah, I'm asking you.
Abdullah is having some problems with his mic.
Okay. Okay, no problem. That's
So yes, let's.
okay, no problem. Okay. Okay. So let's go now. Okay, let's go. Okay. So now let's talk about something. Okay, yeah. So now let's talk about. So Adam, you had a question, right, about this squares, like how can I see squares and things like that. So yeah.
Yeah,
So let's
I
talk about.
asked if a certain shape is always true, no matter
Yeah.
the triangle.
Yeah, and so the answer is yes. So let's see some examples. So yeah. So well, okay. Actually, before we do these, let me just start with the first comment you told us, which was that when we write in an inequality like x minus y squared is greater than or equal to 0, we can see this in the triangle, right? So this is something about degree 2. It's not cyclic or symmetric or anything, but we can still write it. You can write it like this. So this is saying that this inequality is true. Okay. Do you guys see? Yeah. Okay. Right. So when we write that, it means this. So now let's understand this inequality in that term. So okay, first of all, this is one there's many ways to solve this, but let me draw it as a picture. So what does this mean? So we have x squared, y squared, and z squared with 2, 2, and 2, and then we have xy, yz, and xz with minus 2, minus 2, minus 2. Okay, so that's the inequality. But what I want to say is you can break it down like this. You can break it apart as a sum of 3 inequalities. So, or as a sum of 3 expressions where, yeah, so they're going to be like this. So yeah, we have 0, 0, 0, 1, 1, minus 2. That's one term, and then the other term is like this. 1, 1, minus 2, 0, 0, 0. And then we have one last term, which is we will have here, oops, like this, say, oh, no, sorry, not this one. We'll have 0, 0, 0, and 1, 1, minus 2. Okay. So what this is really saying is, okay, whatever this guy on the left-hand side is that you can decompose it as x minus y squared plus x minus z squared plus y minus z squared. And this whole thing is, of course, greater than or equal to 0. Okay. So, okay, this wasn't particularly insightful, but at least does it make sense pictorially what we did?
Yeah, it does.
Okay. So now let's apply it to somewhere where it's a little bit more complicated. So let's look at this inequality here. So
Can I ask a small question for?
yeah, of course, yeah.
On actual Olympiads, if we want to do this, is it just sufficient to do the triangle, or do we actually or after the triangle, we have to show the inequality that it's that,
yeah,
improve it?
So the triangle is a technique. You can't you can't submit it as a proof. You have to basically do this. So the triangle will help you find the correct factorization or it'll help you discover that something can be proved using AMGN, but you can't actually submit the triangle as proof. That's yeah. Karim, did you have a question? Okay, so let's look at the next one. So here, what's happening? I'm going to go ahead and multiply by 3 on both sides, and then oh, wait a second, that doesn't make any sense. Oh, there should be a square. Yeah, right. Okay, now it's homogeneous. And let's just make sure it has the right number of terms. So if we plug in 1, we get 9, so we get 6 on this side and 6 on this side. Okay, great. So yeah, it's the correct number of terms and it's homogeneous. So let's okay, you know what? I'm gonna just copy it. I don't want to do this. So this is what it ends up being when you expand it. Okay, so sorry, I'm not too fond of doing things like that. So what I've done here, I've just taken the inequality, I multiply both sides by 3, and I just expand it, and it becomes this inequality. Nothing clever was done. Okay. Now, looking at this picture, can you maybe see how you might prove it? My claim is you can identify this pattern that we used before. You can identify this pattern in this picture.
Actually, I said each red point is it's like the midpoint of 2 other points, and these 2 other points, when we take their average, we will get minus that red point.
Yeah, so you're noticing these patterns, right?
Yeah.
So these patterns are very close to 1 minus 2, 1. They're not quite. So is there something we can do? So
Can't we split the triangle? Like
yeah,
we
so how
can
do you want to
keep
split
it.
it?
So what do we have? It's 2, 2, 2. So luckily the midpoints are 4, so we can always take a 2 minus 2 and 2. So it would leave us with a triangle that's 2 minus 2, 2 minus 2, 2, and the cyclic of it, plus another one that's 0 minus 1, and that's it, and it's also cyclic.
So you're proposing taking 2 minus 2, 2 from here?
No, from the sides.
From here, each of these.
Yeah, we take 2 minus 2 from all of those. Then we're left with 4 minus 1s, which would be minus a cubed b minus a
so if
cubed c, so on.
So you're saying I extract some pattern like this from there? Yeah, so let's do this. So let me
So it would be 4.
yes.
The mid one would be 4, since we can just take it completely.
Actually, so let me just write something. So okay, if you do this, to divide something else, like so. Yeah. So if you do it like this, I think what happens? So now
I think the middle black points should be 4, since we're using it twice.
but okay, if you got 4, but why do you want to take a 1 minus 2, 1, right? That's what you should, like, you see, like, you want to remove things that you know are positive.
All right, it's 1 minus 2 and not 2, 2.
Yeah,
I looked at
it's 1
I
minus 2.
looked at that triangle now. Okay.
Yeah. So you're using this shape, right? Because this shape we know is oops. This shape we know is an inequality, right? It's valid inequality. So if you remove, like from each of these, you remove 1 minus 2, 1, you're actually in total, you're removing this, right? So this is like I removed 1 minus 2, 1 in from like here,
Yeah.
here. Okay, and what's left? And what's left is very nice. So what's left is now minus 1, 2, 1. Okay, so it's okay. What's left is, unfortunately, it's the wrong sign, but maybe that's okay. So it's like this, right? It's like this. Now, okay, let's think for a little bit. So certainly this is greater than or equal to 0, but this one is actually the opposite sign, right? This is not, this one is negative.
Mm-hmm.
But we can actually do something with this because what is going on here? This one, oops, I wanted the pointer. So this one, I can like, okay, I can write everything very nicely. So I can say, I have, like let's think about this edge. This edge, I have 1 factor plus 1 factor minus another factor. So that edge, for example, I can write it as, I have x minus y squared. That's okay. Sorry, let's move that here. So I have minus x minus y squared. And then I have that thing, sorry, let me think a little bit. So so these are degree 4, so it should be minus x minus y squared times xy. And then here I have x squared plus y squared times x minus y squared. And then everything is summed cyclically. Yeah. Does that make sense? What we did here? So I'm interpreting this edge. So here we have x squared times x minus y squared. Here we have y squared times x minus y squared. And then here we have negative xy times x minus y squared. Does that make sense? Do you guys follow?
Yeah.
Okay, and so then what does this mean? So it means that I mean then it actually this just follows, right? So I factor out x minus y squared and I have x squared minus xy plus y squared. But okay. This is greater than or equal to 0, but this one is actually also greater than or equal to 0 because it's like what is this? This is equal to x minus y. Yeah, exactly. It's like the sum of something non-negative and something non-negative. So okay. So then this whole thing is greater than or equal to 0. Does it make sense?
Yeah, it does.
Okay. Okay. Yeah, so really the thing was understanding like, okay, what's going on this outside is we're just adding a bunch of small blocks that are all looking like this. Like it's this triangle is a sum of 9 blocks that look like this. Yeah. Okay. Okay, now let's do Schur's inequality. Okay, right. Actually, before I go on, are there any questions about this argument here? Anything that wasn't clear?
But why when we add the sum block of this one, we must have it to be bigger than or equal to 0.
You're asking why? Okay, are you asking why this is? You're asking why I could add something positive and something negative to get something positive?
No, I don't mean this. I mean that the first block that we have showed that it's bigger than or equal to 0, x minus y squared. Why it works that when we add it like in more complicated diagram like this, it will be bigger than or equal to 0. It's a different diagram.
Well, because what is this really telling us? It's telling us that this thing, if you expand it, right? If you expand it, something like 2x to the fourth plus 2y to the fourth plus 2, whatever. Like there's some polynomial here. If you expand it, it actually is equal to this. That's what this equation of pictures. It's saying that this polynomial equals this. But this is greater than or equal to 0 because you can just see, right? Does it make sense?
Yeah.
Like
but
when
I think I mean something different. Like when we see, I think we have assumed that when we see 1 minus 2, 1 this block, and this other diagram, then it will be bigger than or equal to 0.
So you're asking like you're asking like if I ever see this shape in some weird orientation, why is it non-negative? Is this the question?
Yes.
Yeah, so let's see. So let's say I do something. I have let's say it's let me think what I can do. Let's do something a little weird. So let's do in kind of a strange orientation. So let's do something like this. Kind of a weird orientation, right? So this even, what is it? So let's draw it 1, 1, minus 2, and let's decide what the size is. So let's decide that it's this size. Okay, so it's 0, 1, 2, 3. It's a fourth degree polynomial, and what is it? It's y to the fourth, and then the minus 2 times what? So minus 2 times so it'll be minus 2 times so there'll be 1x, and then there'll be y cubed z, no, y squared z, right? Yeah. Is that right? So yeah, and then plus, then this one will have only x and z, so it'll be x squared z squared. Is that right? Yeah. Right? That's what that is. Do you see how to write this as a square? This is equal to y squared minus xz all squared. So whenever you see this shape, you can always write it as a square. Or okay, like okay, it might be that it's off center. So like, you know, if you find this shape, like in this case, right? Like in this case, the shape is, no, that's okay. What do I mean? Like in these cases, the shape is off center. So it's like, it's a square times some term, but you can always do that. Does it make sense?
Yes.
Yeah. Okay. And I'll say like pictorially, it's much easier to notice this than it is to look at that and realize it's a square. Okay, that's sort of the point. Okay, now let's go to sure. So sure is an equality. Let's see what it says, and then we'll draw the picture for it. So sure is an equality. Actually, there's many versions. There's there's a parameter r, but okay. So it's saying that for any positive r and any x, y, z greater than or equals 0, this is greater than or equals 0. So this is a theorem. You can take this as a theorem. I won't talk about the proof. If you want, you can ask me. I'll send you something. But for now, let's just take it as a theorem. Okay. And let's try to draw what it means. So I'm just going to rewrite in a way that is in terms of cyclic, directly in terms of cyclic things. So we'll write it as one term which is cyclic, which is cyclic x to the r plus 2, and then another term which is cyclic x to the r y z, and this is greater than or equal to the maybe symmetric now on the other side, x to the r plus 1 y. Okay, so on each side we have 6 terms. So yeah, let's draw the cubic version. So by cubic version I mean r equals 1, so it's a cubic, the degree 3 polynomial. And what it's saying is that I have x cubed plus y cubed plus z cubed, and then now I do cyclic of x, y, z is 3x, y, z is greater than or equal to the symmetric sum of x squared y. Okay, so let's draw the picture. So it looks like this: 3, 2, 1, 2, 1, 0. Yeah, so it's like this and this, and then here we have 3, and then we have, these are all -1. So you actually cannot prove this using any kind of AMGM or anything. But yeah, okay. So this is like a completely independent theorem. You cannot prove it by Muirhead or AMGM. It's not possible, but it's a theorem. Okay. Yeah, so does it make sense what cubic Shiller says? So you can just take it as a black box. The point is, it's helpful in situations where you have some kind of really weak term paired with a very strong term, and then you want to say something because this is very hard to deal with. It's very weak. Okay, and then let me explain the degree 5 version. So the degree 5 version is like this. Okay, so zero, 5, 4, 3, 2. I believe it's like this. And the rest are 0. Okay, so great. Yeah, it looks like this. Yeah, so there's so the corners are x to the r plus 2, and then you have the red, which is this, and then you have the 3 terms, which are this. So in general, you see like what is the pattern? So the pattern is like you have some kind of like diamonds on the corners, and that's if you increase r, that's just what the inequality is saying. You have these diamonds on the corners, and this is always greater than or equal to 0. Okay, so does the statement of Schur's inequality make sense?
Yeah.
Okay. Okay. Okay, so maybe I'll just do one example and then we can see. So the example is this. You have something like this. This is your inequality. Okay. There's clever ways to solve this, but let's say you just wanted to expand and see what happens. So if you expand and you homogenize using the constraint, you actually get this inequality. okay, this is kind of a crazy inequality, but let's it's crazy, and it's like, okay, if you look at this, I have no idea whether it's AMGM or sure or anything like that. But let's draw the picture. So yeah, so it's going to be degree 6. So great. So 0, 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. We'll have zeros. And then I'll have 6 below. And then x to the 4th y squared. So I'll have these, which are 1. And then, okay, so then x cubed y cubed. So, okay, these terms are going to be on the boundary, and they're going to be midpoints of the edges. So they're here, here, and here. And so they're 2, 2, and 2. And then, yeah, so then let's talk about the, sorry, those are the wrong color. 2, 2, and 2. And then, okay, so now what about the other terms? So x to the 4th yz is going to be, okay, so this is x to the 6th, this is x to the 0. So x to the 4th is here, which means this is x to the 4th yz. And the cyclic terms are there. And then x squared y squared z squared. Sorry, what did I write? That doesn't make sense. I want to say that they're here, but I don't know how that happened. Yeah, it's because I wrote something wrong. So this one is x cubed yz. Yeah, there we go. And this term is x cubed yz. Yeah, that makes sense. X cubed y squared z. Okay. So yeah, so we get this one here. Yeah, so all the red is -2, and then we have like 1, 2, 1, and 6. Okay. So yeah, does it make sense what the picture is? So I'm gonna copy Zero's inequality over and see if you can find it in the picture. So here you have this. So here is cubic Schur's inequality, and here is the inequality you want to prove. Okay.
It's there in reverse or upward,
Yeah.
upside down.
Yeah, so that's the point. It's here, right?
And we have the one -2, 1, which we already know is true.
Great. So
And
yeah,
three
we have
small
these.
triangles.
Great. Yeah. So actually, that proves it. So here we have Schur, and then we have sum of squares. So how would you prove this? Well, okay, so the point is, what's the Schur? So the Schur is now, it's Schur's inequality, but how do we write it?
We have to flip to move the variables one. For example, A must become B and C must become A and so on.
So if you cyclically shift the variables, that'll just rotate the triangle 120 degrees. It won't change anything. right? Sure
Oh
is
yeah,
already a
right.
cycle, right? So what does it mean when you invert? What it means is the following. So it means that instead of being an inequality about so instead of being it means that instead of being about A, B, and C, or sorry, about X, Y, and Z,
Is it about A,
inequality.
B, B, C, C, A?
Yeah, exactly. That's what it means. So it means that, whatever. So sure, what was sure? So sure was like cyclic sum of X times X minus Y times Y minus Z, because it's the cubic one. So sorry. Let me just say it correctly. So sure is about the cyclic sum of X times X minus Y times X minus Z, and we know it's greater than or equal to 0. So here you're going to have the cyclic sum of XY minus XZ, and XY minus YZ. That'll be the short in the middle, and then of course you have the squares. And so what are the squares? They're give with me so that I can figure out what the squares are. So they're okay, let's just figure out one. So one of them is going to be x to the power 4. They're all x to the power 4. And then y minus z squared, I think. Yeah, so x to the 4, so plus cyclic sum of x to the power 4 times y minus z squared. This is what these will be. And then that's greater than or equal to 0 by sure. Yeah. Okay. Any questions about this one? So I think, it's really impossible to recognize this as sure as inequality unless you write the, the picture. Then it's clear. Good.
How could we prove that whenever we see, like, when we know that when that this triangle represents quality that it's always bigger than or equal to 0, and then we see it in another triangle, which is different, which is different. How can we prove that whenever we see it, it must represent it's bigger than or equal to 0 for some like part of that inequality?
Yeah, so you're saying if I have a valid inequality and then I move it around or I rotate it, why is it true?
Yeah,
So,
or I put it in a part in a bigger triangle.
well, okay, when I have a bigger triangle, my goal always is to decompose into pieces that are true, right? Like,
But
so
why this work?
what?
Could we have an argument to prove that this work?
Which one? The decomposing part or the moving it around?
Decomposing the bigger triangle.
Well, if you decompose the bigger triangle into inequalities that are true, then you can just it's true because you can write this as this plus this. Right? Like if I just write if I write the thing instead of writing greater than or equal to, I write minus. Right? I'm just saying that this is equal to this. So if each of these is greater than or equal to 0, then their sum is greater than or equal to 0. Does that make sense?
Yes.
So the decomposition is just because I've decomposed my expression as a sum. Okay. But the other thing is, why can I move these triangles around? So okay, first of all, moving around, all it does is it multiplies by some monomial. So like, when I write y minus z squared is just something like this. 1 minus 2, 1. But now when it shows up here, it's y minus z squared, here, it's y minus z squared times x to the 4th. So when I translate it, I'm just adding some factor. So that's still going to be non-negative. The other thing is, what if I rotate? This was more complicated, but you can also show a rotation is always a change of variables. That's always true. So for example, when you flipped it upside down, it just means you change from variables x, y, z to x, y, y, z, x, z. That's always going to be true. And you have to figure out what the change of variables are. But it will always be true. Does that answer your question, Carl?
Yeah.
Okay. Okay, so I wanted to explain one more thing. It's a little important, so let's talk about it. So I wanted to talk about, this will have to be brief because we don't have much time, but maybe in 10 minutes I can try to explain this. So I'm going to consider what I call compound inequalities. So these are a little bit, these are inequalities where you want to use AMGM, but it's not something simple, like where I have one symmetric compared to one other symmetric. It's like you'll see what I mean. So it came from this one, which was on the homework. Yeah, so this was, maybe you can remember, this was from the homework. And so what I'm going to do is I'm going to do nothing at all very clever. I'm just going to completely multiply everything out. And I'll make the substitution x, y, z are a to the 1/3, b to the 1/3, and c to the 1/3, so that the exponents are all integers. But it's not necessary to do that. It's just I do it so it makes things easier. Okay, and what you arrive at is this inequality. Okay, so on the left-hand side you have 3 types of terms, and on the right-hand side you have 1. And okay, we'll see when we draw it, but like these are strong terms and this is like completely weak. It's in the center, and then you have this here. Yeah, okay, great. And so there's 3, 3, 3, 9 terms here and 9 terms there. So it's okay. So 9 terms, degree 12. So when we draw the picture, I'm going to actually just copy the picture from here. So I'm going to copy the picture from here. Yeah. Let's go back now. So I claim that this picture is for this inequality, right? And yeah, so it's degree 12. So I drew the vertices x to the 12, y to the 12, and z to the 12. And then what? So then, oops, that's what I want. Okay, so this term gives you the 6 terms here. Oh, no, it does not. It gives you, so yeah, so this one gives you this one, and this one, okay? So yeah, it's a cyclic sum, so you get 3 in an equilateral triangle. And then this one gives you the 3 midpoints of the sides. This gives you the center, and then these give you some kind of weird terms, but you can sort of see where they lie, right? So this is x to the 6th, so it lies between x to the 12 and x to the 0, so it lies on this, and it lies on the midpoint of that segment. Okay. Okay. So I don't think you can prove this using sure or some of squares anyway. Maybe you can. But what you can do is you can use weighted AMGM, but you have to understand how do I use weighted AMGM? Because you see, like I'm trying to compare 3 cyclic sums versus 1. So it's like, what can I do? So yeah. So if I tried to use weighted AMGM, I would need to do something like this. I would need to say something like I'd somehow have to weight all 9 terms against to get 1. So I should say, okay, W1 x to the 9 z cubed plus W2 y to the 9 x cubed plus W3 z to the 9 y cubed plus W4 x to the 6 z to the 6 plus W5 x to the 6 y to the 6 plus W6 times z to the 6th x y to the 6th plus say W7 times x to the 4, y to the 4, z to the 4. And I want to basically argue that this is this. Okay. And then I sum cyclic. So then I basically I take cyclic sum and I get whatever. But now let me ask something. If I do a proof like this, what condition, like there are some conditions I will have to impose on the weights. Like I can't just have an arbitrary weights here. So for this proof to work, I can't just put arbitrary weights.
Since we take the cyclic sum and multiply it by 3, they almost no weight no group of weights must be bigger than 1/3. They all must be in that range. So every 3 weights must be equal to 1/3 instead of 1.
Yeah. So the point is all these weights they add to 1, but actually these 3 add to 1/3, these 3 add to 1/3, and this is exactly 1/3. Does it make sense? So let me write the condition that Abraham just explained. The point is that we must have W1 plus W2 plus W3 is 1/3, and then W4 plus W5 plus W6 is 1/3, and W7 is 1/3. Because what we're going to do is we're going to take cyclic sums of this, add them together, and multiply the whole thing by 3 to get this inequality. And so, like, the coefficient of this will only know about W1, W2, and W3, right? Does it make sense what I'm saying? You guys understand what?
Why?
So
Why
so
we-
imagine. Yeah,
Yeah.
why what? Why this condition?
Yeah.
So how would this proof work? So you write this inequality, and then you sum this inequality cyclically, right? So you write the three the two other in it, right? Now when I add them, what do I get? Here I'm going to get x to the 9 times z cubed, but not times w1, w2, w3 all the way to w. I'm not. I will only see here w1 plus w2 plus w3. Right? Like do you see what I'm saying?
You want to apply AMGM on like 3 terms, not on the second.
No. We apply AMGM on all of these terms. Okay, and if we pick the weights correctly, we don't know what they are, but if we pick the weights correctly, we can make this true. But the point is, how does this help you? Like what you do is you write this inequality and you'll write cyclic, like then I'll write the same inequality but cyclically, and then I'll add them all. Does it make sense?
Another way to think about it is all of the weights are lower than 1. So no matter the weights, it's smaller than the inequality we have above. What we want to do is multiply it by 3. But in order to ensure that it's always smaller than the equality above, each w times 3 must be smaller than 1. And the only way to force that is to have w1 plus w2 plus w3 is equal to 1/3.
Let me see if I can figure out what I'm doing. So I think something like this. So what I wrote here is if we have this first inequality by AMGM, so suppose we pick the weight so that this is true by AMGM, then we have this one and we have this one. These are just the same inequality but cyclic, like cyclically permuted. So now when I add them, right, when I add all of these, on the right-hand side, I'll get what I want. I'll get 3 times the So I'll just get 1 times the cyclic sum of x to the 6 y cubed z cubed. But on the left-hand side, I will get each term, but unlike here, I'll get cyclic sum of x to the 9 z cubed times w1 plus w2 plus w3. And I'll get cyclic sum of x to the 6 z to the 6, but times w4 plus w5 plus w6, and so on. And I'll get 3 times w7 x to the 4 y to the 4 z to the 4. So for this to work, like each triple must individually sum to 1/3. Does it make sense? Okay, maybe okay, we're almost out of time, so maybe okay, I'll finish up the explanation and then we can you can ask me if later. But the point is now, like, what really are we doing? What we're doing is we're taking okay, so I'm taking some, oops, I can write it as, okay, so first there's a blue triangle here. There's a blue triangle, oops, what do I want? There's a blue triangle here, and let's say there's a black triangle here. So what I'm doing is I'm trying to write this red point as first I pick a blue triangle, which is some combination of, like, I'm writing it as right, W1, W2. So I'm writing it as some combination, something inside the blue triangle, and I'm taking something inside the black triangle. And then I'm trying to express the red point as the centroid of these three. Does it make sense?
Yes, because it's like 1/3 of the first and plus 1/3 of the second and plus 1/3 of the third.
Yeah, exactly, right. So the result is I need to find a blue point that's inside the triangle, black point inside the triangle, and this, and write as like this. But actually what that means, if you think about it, it just means that if I want to write the red point as a centroid, but okay, but what is the thing about the centroid, right? So if I have a triangle like this, where I have red here, and then I have this and this, and I have the blue one. Okay, you can understand it as if I take this and I extend it to here. So what I've done, I can extend this to here, where the ratio is, where this ratio is 2 to 1. I want this one to be the midpoint of these two. And what is that explicitly? So explicitly, this is, I can see, right? So what is explicitly, this is something like 4, 4, 4. This one is 6, 3, 3. So this one will be 7, 2.5, 2.5. So at some point, you can see where it is. And I want to write it as the midpoint of something in the blue triangle and something in the black triangle. Okay. And then you can see it's explicitly, it's possible. Like I don't know, maybe it's even, you can see it in the picture, right? Like, certainly there's a way to write this point as the midpoint of something in blue and something in black. And okay. Once you find those, then you have the weights. Okay, so I was a little rushed at the end, but does it make sense?
Are there any resources where we can do some further reading?
Yeah. So you want to read about this this Chinese notation. So I looked online. I didn't. Here's what this. I'll find something. Okay. I'll find something about this Chinese inequalities notation. So
I found a source. Evan Chan has an amazing like 11
Okay, great. So maybe
page
can
notes.
can you
I'll
can you
share
share?
it. No worries.
Okay, yeah, please share it. Also, let me